Okay, so we got a solid circular disk with radius 8. The easiest one is to make it on the origin. So the disk could be anywhere, but to make the math the most friendly, I'm going to put it so this is, so what is the equation of this right here? Equals 8 squared, 64. So parallel cross sections perpendicular to the base are squares. So we're going to have, you imagine squares with their base on the disk, and then like in this view they'd be sticking right up at you, right? So then the largest square would be here at the diameter, and then the squares would shrink down to 0 as you got to here. So let's see if I can draw it here. So you're going to have an edge at the corner of these squares as they come down. So you're going to have an edge like this. You can do it. And then another edge up like this. And it's going to look like the same thing on the back side too. So down to here. Like that. Oh, no, sorry. From here. Like that. So it's going to be this rather strange shape. It's going to be curved on the side, but it's going to have a corner like this. And then it's going to be curved down like this with an edge, another edge like that. Okay, so I don't know. You can see that if you get far away from it. Anyway, so we need to do what? We need to add up all the volumes of these squares. And we can make it easier on ourselves. We can go from, so it's going to be delta y or delta x, the way I've drawn it.
Delta y.
It'll be delta y. And then we can go from 0 up to 8, and by symmetry multiply by 2, right? So we need the volume of a typical square. Or tile, I should say, square tile. And so the thickness of it, we've already said, is delta y. So what is the side length of the squares? It's not radius, right? It's from what? It's from here to here. What dimension is that right there?
2 square roots of 25 minus 5 squared.
Start with your easiest possible way to describe that. Is it x? From there to there is x?
2x.
2x, right? From there, so from the y-axis out to here is x. This is twice, so it's going to be 2x, and that thing squared, delta y. Do you see it? Because from here to here is x. And that square is side length is twice as long as that. And then it's going to be 2x on this dimension, 2x on this dimension, and delta y. So so this is basically 4x squared, delta y. So here's a little trick that you can look for. So we need to get x in terms of y. But really, what do we need? We need x squared in terms of y, right? So, giving me weird eyes. Did I lose you? You sure? Okay. You gave me a funny face there. Any questions up to this point? Does it make sense? So normally we would say, okay, we want to get x in terms of y. We want to plug our expression for x in terms of y into here. But really, what do we need? We need x squared for our purposes. We could get x and plug it in and square it, but we just need x squared. What's x squared? It's easier. What is x squared? 64 minus y squared. So that's perfectly legitimate. Because that's what x squared is. X squared is 64 minus y squared. So it saves you taking the square root and then squaring again. And then we're going to add all those up from what to what? Yes, let's make it easy. So 0 to 8. So this is going to make solving nice, right? When we have to do the solving, that's going to be helpful. And then we can just by symmetry say times 2. And what does this whole thing represent right there? That whole thing is? Is it an area? Volume of a typical. So now we're talking about like, it's a really super thin square, right? Because we're going to have like a zillion of these square tiles that are super thin. So this is the volume of one super thin tile square. Okay. Question?
Is it starting from negative 8 or 0?
Okay. So why am I? Someone else. Why am I starting from 0?
Make the math easier, so you can just double it at the end.
Yeah. So it makes my math easier, and then I'm just multiplying by 2, right? This is by symmetry. It's going to be the same volume from 0 to 8 as from negative 8 to 0. So I'm making my life. I'm using symmetry to make my life easier. Other questions on this one? Make sense? I'll draw a better version of this. That's better. Anyway, okay. Next one I want to do is okay, so we'll just have to wait for this here. Come on. There it is. This one. Okay, so we got y equals x to the 6th and sine of pi x over 2. Y equals x to the 6th will look like this. Sine pi x over 2 is basically a version of sine, something like this. Okay, and we want to rotate that about x equals negative 8. And they want us to use shells to do it. Okay, So, is that going to be... Is that going to be, if we take that and rotate it, will we get shells? Or if we take, say, that and rotate it, will we get shells?
Blue.
Blue or red? Blue gives us shells, red gives us
Washers.
washers. Both totally legit, okay? Both legitimate, but they say use shells, and this is the assignment we're practicing that, so we're going to use shells to do it. So we're going to get this, just for the drawing's sake, I'm going to make it a lot closer here. So this is it's not to scale anymore at all. But our shell's going to look like this. Okay, something like that. So we want the volume of a typical shell. And the volume of a shell is going to be, so we got 2 pi r h times the thickness. 2 pi r is the distance around the shell. H is the height. And then the thickness, delta y or delta x? Delta x, right? So we need the radius and the height of this thing. What is the radius of our shell from here to here? Yes, it's going to be this x. This is the x coordinate of both curves, right? It's the x coordinate of both curves. And then we're going to add 8 to that, right? If you want to do x minus negative 8, that's fine, but you know this is going to be, x is going to be over here, and then you're going to have a distance of 8 right there. So x plus 8. H is the height of the shell is from here to here. So that's going to be y2 minus y1. And y2 is going to be? That's the sine graph. And y1, x to the 6th. Delta x. And we're going to add those up from, starting from here, the real short, small ones, all the way to here. So we need an x value for that. So 0 to what? So how are we going to get that x value? Okay, so, and then how the heck do we do that? Use your graphing calculator?
You know that sines always go from 0 to 1.
Okay.
So just find when x to the 6 equals 1. Which is just 1.
What? So sine of pi over 2 is 1. Oh, I see. Okay, so you're saying when x is 1, then they both equal 1.
Yes.
Okay, so it's going to be 0 to 1.
Quick question.
Yeah.
What happened to the sign of 8?
What's that? The line -8?
Yeah.
That's our rotating axis, right? So we're taking this region that I've shaded in black, and we're rotating around the line -8. So that had to do with the radius, right? So that was the radius of our shell. Our radius was 8 plus x. So that was our radius of the shell. But in terms of the bounds, you know, we're going to start with the first shell is there at 0, and the last shell is here at, this is 1. So the bounds has nothing to do with the 8. 8 is what we're rotating around. And the shells, the first little shell is right here, like this. And then we have all the shells starting from 0 all the way to 1. Does it answer it? Other questions? So now this integral. Let's talk about, you're going to have 4 different parts. So x times sine this thing. How do we do the antiderivative of that? For number 1. X times sine of pi over 2x. That's undoing product, right? Undoing product. 8 times sine is easy. X times x to the 6th is x to the 7th. That's easy. And then 8 times x to the 6th is also easy. So you got 3 easy ones, and then the undoing product rule for x times sine x. Questions on this example? Okay, so let's do this. When they get to the back, pass left and right, because thinking nothing will run. So it was shells and then washers. Okay. What should I do? I'll do one of them. Which one should I do? So this is x equals y cubed. And then y equals 1/4 x. And then we're going about y equals -5. Okay, so if we do delta x, shells or washers?
Washers.
That'll be washers, right? That'll be washers. And then if we deal delta y, we'll get shells. What's the consensus? What should I do? All in favor of washers? All in favor of shells? The rest of you don't care. It's like 3 votes. Do you want to do it or not?
Shells.
Shells? Alright, so shells is which? Delta x or delta y? Delta y. And so it's going to look like this. Typical shell. that, okay? And then we're going to add all those up from 0. The first one will be at y equals 0. And then the last one will be at y equals 2. This is the point 8, 2. So we're going to, if we do shells, the first one will be 0 up to 2. Okay, so then our volume of a typical shell is the circumference, 2 pi r, times the height of the shell this way, and we're going to have delta y. So what is the radius of the shell? Well, the radius of the shell would be from, do it in blue, from here to here. That's the radius of the shell. So that's going to be the y-coordinate plus another 5 will be the radius. So 2 pi times y plus 5. And the height of the shell will be this dimension here. So this blue is the radius. And then it's going to be that distance there is the height. So it's going to be like an x2 minus x1. And we got to get each of those in terms of y. So x2 in terms of y. 4y, right? Because the x2 is based on the line. And we'd be x in terms of y. So it'd be 4, this would be 4y. x1 is our y cubed. It's the x coordinate of that in terms of y, which is our y cubed. So we're going to go from, what did we say, 0 to 2. Black. 0 to 2, 2 pi, y plus 5, 4y minus y cubed dy. That would be the shells method. Questions on that? Anybody have a question? Did you get it? Some people are nodding. Close? Close, at least? Most of it? Okay. So what's hard? Is the radius the difficulty or the height the difficulty on this?
It's the height.
The height, this part?
Yeah.
Yeah, so the height is this here. It's going to be a final x minus initial x. And the final x is determined by the line, so x equals 4y. And then the initial x value is the curve, so that's the cube, or y cubed, x equals y cubed. Question? The radius, okay, so the radius is what I've shown in blue here, do you see that? It's from the center of rotation up to the edge of the shell. So that's basically two parts. You've got from the x-axis up to the edge, which is just your y-coordinate, right? That's just the y-coordinate of both curves. And then the rest of the radius is going to be, this is down to negative 5, so that's a distance of 5 right there. It's going to be 5 plus y. Does it help? Other questions? All right, we got time, so we'll set up I'll set up the shells too, or the washers too. So for washers, it's going to be this way. So we're going to have, it's going to look like this. Or something. Okay. And okay, so that's what our washers are going to look like. Okay, and so what's our volume of a typical washer? It's going to be pi outer radius squared times the thickness. What's the thickness this time? Thickness of the washer is a delta x. So pi r squared delta x, that's outer cylinder, minus pi r inner squared delta x. Agree so far? So what's the outer radius? The outer radius is from -5 up to what? The y coordinate of the curve. So it's going to be, again, 5 plus y for the curve. And what's y for the curve? That'd be cube root of x. Okay, that's the outer radius. Equals r outer. And then the inner radius is this one here. So that's going to be 5 plus the y coordinate of the line, which is what? 1/4 x. So we're going to have pi times outer radius is 5 plus cube root of x squared delta x minus pi times inner radius 5 plus 1/4 x squared delta x. And so it's going to be that whole thing in the integral with dx instead. And then what will the limits be? So now we're doing x, right? So it's going to be from 0 to the last x value is 8. Questions on that?
When we set up these integrals, it's fine if we just keep it at 5 plus cube root.
Sure, yeah. All I said was set up an integral for the volume.
Yeah, I just wasn't sure if we wanted to stick to it.
Nope. It just says so. If you just left it like that, would that be an integral for the volume? Yes. So only that you don't need to do anything more than that. Questions on that?
I have a question
Yeah, please.
On the homework.
Yeah.
I got something called quad zero. I didn't know what is that.
It's just 0. So there's an email instructor button on the bottom of each page for the problem, and if you have a question, then just tap that and let me know. You can ask questions about if you're having difficulty with the problem. I watch my email often. So it was just, I don't know what that quad was. It was just 0. So if you just solved it with 0, you got the right answer. Did you ask me about that, right?
Yeah.
And then did it work?
Yeah.
So yeah, if there's bugs or you're having difficulty, use that. You can use that email instructor button. It gives me a link right to your page with your numbers on it. So I can, and I'm watching my email often, so feel free to use that, okay? It's at the bottom of every problem page. Other questions? Okay, let's go on to the next section, which is 7.4. Okay. Okay. So let's take a little walk back in time here through our class. We started by talking about the sum of a bit of change of a quantity and what do we do when we did the integral of a bit of change of a quantity? What do we get? Total change of Q, right? And then we did a rectangle, the sum of a rectangular slice of a region. Area. So area of rectangular slice of a region. And we took the integral of the area of a typical slice of a region. What did we get when we took the integral of that? Total area of the region. Okay, and then we did sum of the typical volume of a disc or washer, and that gave us a total volume. We did the same thing for shell. And that also gives us total volume. Okay? So now if we want to find length of a curve, for instance, say this is some y equals f of x, some function. And we want to get that length right there. It's supposed to stay on the failing. Say from there to there. I want to get the length of that. That's my goal. What am I going to do? What's that?
So we should find the length of the curve from point A to B?
Yeah, how are we going to do that? We're going to sum up bits of something, right? It's going to be doing all semester, right? So this function could be something weird, right? So we don't go to the back of the geometry textbook and say, look for the formula for the length of, x to the 8th over 6 minus pi x to the 7th minus 2x cubed. The geometry textbook's not going to have, if I wanted to find the length of that, say from 1 to 49, you're not going to have a formula in the geometry book, right? This is kind of just a random curve. So we're going to have to do it this way. We're going to have to We're going to have to add up pieces of something, right? We're going to sum up. But what are we going to sum up? Points?
Small length of the curve?
Yeah, so we're going to sum up little itty bitty lengths of the curve. All right? So we're going to break this up into a zillion little pieces, and we're going to add them all up. So what will those pieces be like? Points. So points have no length, right? Points are a location. So it's not points.
Distance between 2 points.
Distance between 2 points. So are those curves or straight segments, right? So it's not going to be a bunch of little curves because that's the whole problem we're trying to find in the first place, is the length of a curve. So we don't know what that is, but we do know how to get the length of a little segment, right? A little line. So that's what we'll do. We're gonna we're gonna break this up. So here I'll just have like That's it's a new picture. But we're gonna add up the sum of segments that are joining points on the curve. Then when those segments we get lots and lots of those segments that are very, very short, that will mimic the actual curve. Okay? So it's going to be the sum, total length of the curve is going to be the sum of a little itty bitty line segment. The highly mathematical term itty bitty. So we're going to sum up lots and lots of little itty bitty line segments that adjoin points along the curve, and if those points are close enough together and those line segments are, microscopic, then it will give us the length of the curve. Okay, so let's see how that works. So say we want from A, this is f of x, and we want from A to B. So like we said, we're going to split this thing up. And we're going to look at line segments. Okay? If we summed up those line segments, would we have an underestimate or an overestimate for the length of the curve? Underestimate, right? Because each one is too short. Because a curve from point to point is going to be a little longer than a short line segment. Okay? So it'll be an underestimate, but as we increase the number of points, that underestimate will get better and better until if we had to kind of think about having many, many points, it would become indistinguishable. The sum of those line segments would be indistinguishable from the length of the curve. Okay, so we're going to look at this. We're going to call each one of these delta S. Okay, because it's not a delta X and it's not a delta Y. So this is like delta S1, delta S2, delta S3, in this case in delta S4. So the sum of the delta S's as I goes from 1 to n is going to be our approximate. And we know it's going to be an underestimate. Right, we're just going to sum up. So it's going to be delta S1 plus delta S2 plus delta S3 plus delta S4, and that we know that summation notation just means sum up a bunch of delta S's. Okay, so what is delta S? So if we look at, just say this is a typical one right here. So we want to get the length of that. How can we get the length of that? How can we?
Square root of the change in x.
Yes, exactly. We're going to use Pythagorean Theorem, right? What is this right here? Delta x. And this is delta y. So this thing becomes delta s is going to be the square root of delta x squared plus delta y squared. Okay, so now thinking ahead, we'd sure like the eventual, so we know this sum is eventually going to become an integral, right? Summing up the finite amount pieces is eventually going to be summing up like an infinite number of little pieces. So it'd really be nice to have our integral in terms of dx. So we're thinking about, we want integral dx, because those are the ones we like. So we'd really like to get this delta x out of here. Okay, so what we can do is, not so much get it out of here, but if we had delta x outside, what we could divide by delta x squared inside. Does that make sense? Because of so it's kind of like doing this. This is 1, right? That's just 1. So I can multiply by that. And then since this is square root, I can combine, get that delta x squared under here. Instead of underneath here, I can get it actually inside. So I'm going to take that delta x squared right there, under the square root, and I'm going to move it inside the square root. Is it fair? And so then what will that give me? And I'm going to distribute. So it's going to give me square root of delta xi and there's our delta x that we like, because that's going to be our dx, right? It's going to be our dx. Did you catch it? Does that make sense? Does it work? Okay, so what about underneath the radical here? What's that? 1. It's nice. 1 plus, what do we have? Delta y over delta x, quantity squared. So inside the square here, delta y over delta x. As delta x gets very, very small, what does that become? No. Oh, someone know that. So as delta x becomes very small, what does the change in y over the change in x become? No. Delta y is going to get small with it, right? What is delta y over delta x? What does it mean? Okay, right. It's the slope of this, or what? The rate of change. So if delta x gets small and delta y gets small with it, what does that become? Ah, so disappointing. Really? Nobody knows? The ratio of delta y to delta x as they get small? Oh. And what is that? I hope someone knows that. The derivative, right? The derivative. It's the derivative, right? It's the derivative. So it's our relative change of y to x, or the slope at any given point, right? The slope at any given point. Instead of just the slope of these tangent these secant segments, it becomes the slope of the curve at any given point. So that's just our derivative. So this whole thing, the sum of, this was just delta s, right? This was just our changing around delta s, becomes the integral of 1 plus derivative squared all square root dx. And so now our bounds, we can go from a to b. because it's in terms of x now. So that's our length of our curve. So this whole thing inside the integral is what? What does that boil down to? In terms of the symbols we have here in the picture. That whole thing is what? No, this inside the integrand. The inside the integrand. Integral of what? What are we summing up? Delta S's? Now they're super small. DS's. That whole thing is ds, right? This was our delta s, which we found was the same as this here, delta s. Let delta x get small, and it becomes this. Well, that's still, we're just summing up. What do we say? A bunch of itty-bitty little line segments to get the total length of the curve. So that, this integral basically boils down to that. It's just we want to get it in terms of x so we can actually solve some problems. Okay? Any questions? Okay, so let's look at some examples. Can I erase this? So, we're going to find the length of the curve. Six x to the 3/2 from 0 less than or equal to x less than or equal to 1. Okay, so our curve length is integral from 0 to 1, 1 plus, so it's going to be dy dx and what is dy dx? Which is what? 18 halves 9 x to the 1/2. Is that right? Squared dx. Okay, so what's that? One plus 81x dx. Can we do it? What do we do? Undo a chain, right? So this is basically g prime of f. So we're going to do antiderivative of g, which is one plus 81x to the, try again, 3/2, and we'll need 2/3. This is what we said was our first attempt, right? So can we imagine if we took the derivative, we'd have an extra factor of 81 when we take the derivative by the chain rule. So we need also here 1/81. Remember doing that? So that's important. 0 to 1. Okay, so what do we got? So this will not be 0 when we plug 0 in. We have to do both, okay? So 2 over, is that 243? 82 to the 3 halves minus 2 over 243, period. Did I do the math right?
Yep.
I plugged 1 in, I get 81, so that's 82 to the 3 halves, and then yeah. And I plug 0 in, I just get 1, and so it's 2 over 243. That's it. So what is that? That's the length of the curve of this function. It's the length of that function starting at x equals 0, ending at 1. That's how long it is, exactly. Okay, so let's. There are some different things that happen here that take some more algebra and some more tricks to get. This one is set up very nicely to make an easy integral, but lots of times, what's under the square root requires some technique in order to get something that we can do. So let's try something a little trickier. Okay, so. Any questions on this? So there's this number 2 in the book. Which says, find length of the curve of, I'll write it out here, y equals square root of 2 minus x squared from 0 to 1. And we can check our answer with geometry. And why can we check our answer with geometry? Do you recognize what you have there?
Circle.
Yeah, so hopefully you recognize that this is actually a semicircle. It's the top half of a circle of radius what? Square root of 2, right? So this would be y squared equals 2 minus x squared, or x squared plus y squared equals 2. So there's a radius of radical 2. So this is radical 2, 0. And so if we're taking from 0 to 1, do you see what part of the curve we're talking about? So can you recognize what part of this curve are we going to be finding the length of? What part of the circle? From where to where? No, not from negative radical 2 to radical 2. So because we're finding the length of the curve from x equals 0 to x equals 1. So what part of this curve is that?
The first one.
First quadrant? Starting at
0.
the top of the circle, right? And then going to 1. So 1, what's special about 1 here for this circle? Where's that going to stop me? So how much of a circle will that be? It can't be about.
45?
What's that?
45 degrees?
Yeah, so it's going to be, this is going to be 1/2 of 1/4 of the circle, right? Because this ratio 1 to radical 2 is the same ratio of radical 2 to 2, which is our pi over 4 angle, or 45 degree angle. So this is going to be 1/8 of the circumference. And that's how we can check it with geometry. So we're going to do it using the line segment formula, and then we'll do the circumference and take 1/8 of it and show that they're the same. Okay? So, but this integral gets a little tricky. There's some stuff we got to do. Okay, so can we set up the integral? See if you can set up the integral for the arc length. I'll let you do it. Everyone do it. Okay, Martin, did you get it? Just the integral? Did you set up the integral?
No, not yet.
Can you just get some of it?
Yeah. I got like the part which is below the square root of the square root
Square root.
will be 2 minus x squared plus 1. The whole will be divided by 2 minus x squared.
Let's just the first step, the very first step.
1 minus 2x.
2x. No, what is our formula? 1 plus what? The derivative squared, right? The derivative squared. Isaiah, did you get the derivative squared? Did you get the derivative? You have to take the derivative of the function, right? And then we're going to square that, and then it's going to be dx. Justin, did you get it?
Yeah. It's I got negative x times 2 minus x squared to the negative 1/2.
That's right. That's what you should have gotten. Okay, because we're going to have 1 over 2 times the radical of this thing, and then times negative 2x. And then your 2's cancel. So that's the derivative, dy dx, for that. Make sense? Okay, so this takes some work. So here we go. Ready? So we're going to have from 0 to 1. We're going to square that first. So 1 plus x squared over 2 minus x squared. Good so far? So what do we want to do? We want to make this all into one term. So we're going to need a common denominator, which is 2 minus x squared. So we're going to get 2 minus x squared plus x squared all over 2 minus x squared. Okay, and so then we're going to have radical 2 over good so far? So now we have to see this as a derivative in disguise. So how can we change this to get it to be like a derivative that we know? Does anyone recognize what derivative this is like? Some of you are saying it. Is it arctangent? No, because arc sine, okay? Arc sine, the derivative of arc sine is 1 over, I'll just write it over here, 1 over square root of 1 minus x squared. So this has to be a 1, or else it's not the derivative of arc sine. So that's going to be our trick. We're going to have to make that into a 1. This radical, so first of all, we can do it as the quotient of the two different square roots. And the numerator is no problem. It's just a factor of radical 2 comes out and leaves us 1. Okay, so that's piece of cake, right? It's this that we have to take care of. So what do we have to do? We have to make that a 1. How do we make that a 1? So we can divide that by 2, but then we've got to compensate for that. So if I divide by 2, then I divide this. So if I divide that whole interior by 2, like that, but isn't that really divided by square root of 2? Because it's underneath the square root. You see that? So then I can, to compensate, then I can multiply by square root of 2. That's in the denominator. Okay, so it's like I took the denominator and it's like I divided by square root of 2 by dividing by 2 inside the square root, and then to compensate for that, I multiply by square root of 2. Is it okay? See, what I really did right here was I divided the denominator by square root of 2. By injecting 2's underneath the square root, I really divided by square root of 2. So then if I just multiply by square root of 2, that's 1. And I didn't change the value. Okay, well then that's nice because this goes away and this goes away. Right? We're having fun now. Okay, 1 over, what do we got? Square root of 1 minus, now we need this to truly be sine inverse. What is it squared? Not x over 4. X over
2.
Radical 2. Because if I square this, I ought to get this right here, right? If I square x over radical 2, I get x squared over 2. That's what I want. See that? And now we got it sine inverse, but it's with undoing the chain too, because we got this little factor on the x squared. So this is equal to sine inverse of what? X over rad 2. Can you imagine that kind of as a first attempt? If we were to take the derivative of that, we would also have if we took the derivative of that, we'd get this, but in addition, we'd also have times 1 over square root of 2. So to compensate for that, multiply by square root of 2. And that from 0 to 1. Did you catch everything? Fun with algebra. Okay, so now we got the square root of 2 sine inverse of 1 over radical 2 minus radical 2 sine inverse of 0. So we're asking what angle gives us a sine of 1 over radical 2, which is the same as radical 2 over 2. So what angle, this is inverse sine, so this is like the output of sine. It's radical 2 over 2. What angle gives us a sine of radical 2 over 2? Right, pi over 4. And what angle gives us a sine of 0? 0. So we got that arc length is radical 2 pi over 4. Okay, so that ought to be 1/8 of the circumference of the circle. What's the circumference equal to? 2 pi r. So what's our circumference? What's this, our radius? Square root of 2 is 1/8 of that, this. If we took 1/8 of that circumference, what do we get this? Yes, 1/8 of the circumference is 2 pi radical 2 over 8, which is pi radical 2 over 4. Check. Any questions? Yeah.
I'm confused how you got on that like second class step there. You got the inverse sine of 1 over square root of 2 into square root of 2 over 2.
So that if you just multiply by square root of 2 over square root of 2, that's going to get you square root of 2 over 2. So 1 over square root of 2 is equal to square root of 2 over 2. If you just multiply top and bottom, rationalize the denominator. If you rationalize the denominator, you get exactly that. Yeah. And so now we're asking what angle gives us that sine, which is pi over 4. Other questions? Okay, another thing that comes up in these integrals is completing the square. So let's try one of those. Can I erase this? So let's try this one. Y equals from 1 to 2. So we've got some cubic curve here. Actually, cubic and 1 over x. And we're going to find the length from 1 to 2. Okay? So we're going to try set up the integral. So you guys set up the integral. So you can do better this time. What integral will give us the length of that curve? Okay, is this Ali right here? Did you get it? Tell me.
I didn't get.
Can you just get started? What will the overall structure of it be?
Square root
Square root?
1. That's the square root of
1 plus the square root?
no, I mean the
X squared.
derivative of y is
Okay. Derivative, which is
x squared
x squared
plus 1 over 4 minus
minus
1 over y
to the
2.
okay. Is that it? And that thing squared, right? The derivative squared. How we do? Is it right? And we're going to do that from 1 to 2. Agree with the derivative and the setup? Agree with that? Okay, here we go. So we're going to expand this and try to get something we can do, okay? So we're going to have 1 plus x to the 4th minus 1/2 plus 1/16 over x to the 4th. Did I do the math? Did I expand right? Middle term will be 2 times that times that. So basically 2 times negative 1/4, negative 1/2. Good? Stop me if I lose you.
How do you get that up?
So when you do FOIL, when you do a binomial square, it's 2 times that, right? So it's that squared plus 2 times that plus that squared.
Oh, okay.
So it's going to be, the x squareds just go away. It's going to be 2 times negative 1/4, which is negative 1/2. All right, so simplify that on the inside. And we'll have x to the 4th, what, plus 1/2, plus 1 over 16, x to the 4th, dx.